Hello? You hear me? You hear me? Yes. The problem is that it connects to my audiphones. All right. So um, let me get started with. So today uh, I'm going to get a bit more serious. So let's talk about high pressure gas xenon TPCs. But let's talk about fundamental things. Now, uh, before we, let me see. Before we talk about the detector, we need to understand uh, why we can build a detector out of xenon. So recall again, what is nice about xenon is that it's a noble gas. Because it's a noble gas, it does not, the electrons, when you ionize the gas, will not recombine. All right? Now, the first thing you want to know is how many electrons, actually electron pairs, you're going to produce when you deposit a given energy. And it is, obviously, you can make this little calculation, and it says that the number of electrons, of course, this is an average, will be the energy that you deposit over a quantity that represents, again, the average response of the medium to the ionization. And this energy is 21.9 electron volts. So the first obvious question that you want to answer is how many ion pairs, electron ion pairs I'm going to have if I am studying neutrinoless double beta decay, and the endpoint I am looking for, I'm interested on what? On 2.5 MeV. So 2.5 MeV is 2.5 million, right? And this is like 2 over 2. So we are over 20. So we are producing order what? 10 to the 5 electrons? It's a lot, okay? It's a lot, but maybe not that much. Now, this is an interesting number that I need you to keep in mind because it's telling you that, first of all, you can do physics with this. This is a big signal. Second, if you introduce 10 to the 5 electrons to an electric current or a voltage, it's not that much. So maybe you need some sort of amplification. All right? So keep that in mind. Now, second thing is that we know that xenon scintillates. And it scintillates with a rather hard ultraviolet light of 172 nanometers, rather fast, of the order of tens of nanoseconds. Now again, we need to know how many photons we will produce on average. Same thing, the energy we deposit over a number that has been measured order 170 something. So notice that we are producing less photons than we are producing electrons, okay? So measuring the scintillation also becomes sort of non-trivial. Notice that when we discuss resolution, which is again one of the names of the game, we want to be able to measure both quantities with small statistical error. And small statistical error means large numbers. In the case of ionization, we can always do amplification. In the case of scintillation, we cannot. So in the case of scintillation, we need to be able to recover as much as that scintillation as possible. Everybody gets the basics? It's all simple. Now, doesn't move. Holy. Why it doesn't move? Okay. Now, we were talking about scintillation. Wow. What are they? Zoom, share, and there we go here, and again, and maybe this time, yes. Okay, we were talking about ionization, and now comes an idea that is quite crucial, and that it was developed actually in a totally different context of what we are attempting to do here. In 1967, by the way, is the same year that Fiorini et al. Were publishing their papers on the first germanium detectors. So Conde and Policarpo came up with a very interesting concept that they called the gas proportional scintillation chamber. So what they discovered is that you can build this little chamber in which you let an X-ray that was intended to measure X-rays. So you make a little window, the X-ray goes in, it interacts in a region where they put a soft electric field. So what happens is that you produce, again, primary electrons. You know how to compute those primary electrons already, right? And then the electric field could drift the electrons softly in a small region to a metallic grid. A metallic grid is a grid where it's like a Gruyere, right? You make many, many holes. And between these two grids, you put an electric field which is more intense than the drift field. So when the electrons cross that region, they accelerate. They accelerate enough to produce UV light, but not enough to break the gas. If you put too much acceleration, you will produce a spark. You will break the gas, and then you will produce an avalanche. If you don't produce an avalanche, you produce proportional scintillation light. And this is the crucial idea. The crucial idea is that when I have an electric field of the order of a few kilovolts per centimeter per bar, which means the more pressure you put, the more voltage you need, okay? And the more wide you make this grid, the more voltage you need. What happens is that you produce a lot of scintillation light. And what is crucial about this scintillation light is that it's proportional. It means that every electron will produce, on average, so many photons. And so now we have an amplification mechanism. Okay? What is nice about this amplification mechanism? That it is proportional, and therefore the fluctuations associated to that mechanism are small. Okay, so you can compute the electroluminescence yield. Most of this work has been done by the next collaboration, so on. So we did this work both in Monte Carlo and doing calculations and doing little experiments. And what you get is that the yield normalized to the pressure. So the number of photons that you're going to get normalized to the pressure is going to be proportional to the electric field. Normalized to the pressure again, it's a number 100 times. So get your time. Yield 100 times electric field for a given pressure minus something, which means that I'm, in average, able to amplify by 2 orders of magnitude my signal. Whoa, nice. So if I have 100,000 electrons and I amplify by 2 orders of magnitude, I end up with 10 to the 7 electrons. This is nice. I can make a nice signal out of that. Okay? So, of course, everything is reduced, which means that as you increase pressure in one thing, you need to take this pressure into account. And we now have the ingredients to discuss TPCs. So TPC stands for time projection chamber, and the time projection chamber was invented by Dave Nygren, my mentor, co-spokesperson of NX for many years before he decided to retire. What we say is that he didn't retire, he ascended to paradise, more or less. He's still on Earth. And one of the best physicists, certainly, of the last decades. So Dave invented the TPC in the 70s, and he has told me many times that when he was interviewed at the beginning by journalists, most of them understood what a TPC was, but one of them asked him once, and so with your time projection chamber, you project to the future or to the past? So he didn't quite project himself to the future or to the past. But the idea of the TPC, it is beautiful, elegant. What you do is you take a volume, you put some rings. All these rings, you connect them with resistors, and then you make an uniform electric field. Now, when you ionize the gas, now you will have a particle will go through, you will make electrons and pairs, and ions will drift into one thing, and the electrons will drift in the opposite direction. So you end up being able, of course, if now you segment the anode or segment the cathode, which eventually you can segment the anode for the electrons with pads. Now, you add everything that comes into the pads after you amplify, and you have a measurement of the energy, and the pads will tell you the position in XY, right? But if you can measure the time of drift is now proportional to the third coordinate. So now you have a 3D detector. So this 3D detector is one of the most useful systems ever invented in particle physics. It's being used all over the place. For some mysterious reason, they've never got a Nobel Prize for that, but it's not too late. So stay with me. My own bet is that it will still happen and in less than 10 years. Okay, mark my words. Okay, record, it's on record. So what is the next concept? The next concept combines two ideas that we have discussed first. The idea of the gas proportional chamber. Second, the idea of the TPC. So let's go through the movements. What you do in the case of NEX is that you have an electron or two electrons that propagate in the gas. You have electrons that drift to the anode. When they get to the anode, they are accelerated between two grids and they produce photons. Okay? Now, notice that when the interaction itself happens, fast scintillation will happen immediately. So suppose that we are recording the signals. So this is the first thing that we see. Nothing, 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 nothing. Something happened. Fast interaction, not much, but very sharp. What is this thing telling me? Start of the event, T0. All right? Then wait. Why are you waiting? Because electrons are drifting. Okay? How fast these guys move? These guys move about 1 microsecond, 1 millimeter per microsecond. So it will take them, a few hundred of microseconds to get there to the anode. And in the anode, they get amplified. And then you get a signal. Why is this signal so funny? Because I have an extended track. And as the electron goes through, imagine this electron being eaten by the grid, you get keeping signal. This is one of the blobs. This is one of the extremes of the blob. This could be another. So you get a quick signal, which we call S1, a delayed signal that we call S2. Now, if you integrate that signal, what do you get? The energy of the event, right? And because the signal is very much amplified, you expect it to be really good resolution. We still need to demonstrate that. It looks like, right? But what else? Because I know the difference between S1 and S2, I know where my event is. So now my event is localized in Z, in time. And if I put here a pad system, then I have the 2 dimension. But something else. Have you noticed that the only signals that I'm reading is light? This is a light TPC. It's a beautiful object. It only reads light. It doesn't give a damn about anything else. So you put silicon PMs here, and then you have a way to measure position. And you want to integrate this thing. So the first thing we could do, kind of easy, we put photomultipliers all over the place. Why photomultipliers? Because these guys are good to measure signals. These guys, by the way, will measure S1 very quickly too. So here you have the concept. You have a nice gas volume, you have an EL region, you have silicon PNs, photomultipliers S1, S2. I will tell you more later. But this was drawn in Berkeley about 15 years ago over coffee. And for some reason that I don't understand, people, to these kind of ideas that you draw in a bar, people call back in the envelope in English. Well, I have never seen anyone making these drawings in an envelope. But for sure they do this, in a napkin. So I do propose, it is called back of the napkin. I have still the original napkin in my pocket somewhere. But this was sort of the make it clean drawing. I'll come back to this. Meanwhile, we have understood the idea, so this is just repeating the same thing. And these are the kind of numbers that we discuss. So before we go further, we still need to give one missing number here. I've told you that we amplify, so we can transform ionization in light, but then we need to recover the light. So how do we measure the light? Silicon PMs or photomultipliers. But this light is 172 nanometers, so hard like hell. So here we have two ways of doing things. Either we put PMTs and photomultipliers that are sensitive to such a hard VUV, which is nice, but it has a number of problems. The problems, first of all, is that these objects are more expensive because they are sensitive to VUV. The second is that you would just be, your light collection would be limited, right? Because only the light going here or here would be useful. The light that goes there will probably not be recovered because at 172 nanometers, you don't recover that much. Although you do. I mean, you could put Teflon, and Teflon will recover quite a bit of the VUV light, but not that much. After a few goings around, you lose the light. So what happens is that if you use VUV sensors, your light collection as a total is not great. So you have an alternative, and this is a messy alternative. Okay? So this is the typical solution in which you feel, your patient comes with a headache and you fix it by cutting his head or her head, right? You can put TPB. What is TPB? Tetraphenylbutadiene. You can put TPB all over the place. Now, hell, believe me, messy. You evaporate TPV, and TPV is a molecule that will absorb 172 nanometers radiation and will re-emit on the blue, about 400 and something. It's almost violet, yeah, already. It is violet. But at 400 something, you can do normal sensors, not a problem. Also, if you put a light tube, so you have your PMTs, you have silicon PMs, your light tube, now you make it of Teflon, and Teflon will have a great reflectivity at this wavelength. So what you achieve is that your light collection becomes better. And when I say better, it's 1%. It's not that you have 70%. 1% of light collection means that out of your 10 to the 7 photons, you're just picking up 10 to the 5. But 10 to the 5 photons, if you take the square root of that, it's a very small number. So I have enough light that at Q beta beta at the endpoint, I don't have a problem with resolution associated to photon statistics. Agreed? Now, what is the price to pay? Messy TPV all over the place. Okay? You have to throw TPV to your thing. Okay, this is called a compromise. Okay? Now, The other thing that we didn't, so we kind of get the idea in the head, like tracking, energy collection, we have the numbers, but we still need to understand, I mean, what is kind of nice about a high pressure gas TPC? Why, by the way, high pressure? Why shouldn't I do it normal pressure TPC? Why would you think I need to put 10 bars or 15 bars or 20 bars of pressure on my detector? What is your argument? No, you don't say anything. You know everything. For the mass, obviously, right? I mean, come on. I need the mass. And if I put 10 bars, 10 times more. If I put 20 bars, 20 times. So I need the mass. So this is the reason why I put the mass. Now, because I'm putting the mass, the method, the guy is more dense. So now, what about the track? Imagine that we have this 2-electron thing, right? Let's think a little bit about the physics here. So I have these 2 electrons propagating through the gas. What do you guys expect? Obvious question. Can I measure the vertex? I want a quick answer. Not you. Can I measure the vertex of the 2 electrons? You know, I have the 2 electrons. One will go this direction, the other one will this direction. Some of them will come with very violent angles. Can I measure it? Give me an answer. No? Why? Multiple scattering? Why? Exactly. The thing scatters like hell. A price to pay. Thing scatters like hell, and then what I see is a wire. And I cannot see the original vertex because the thing can scatter more than the original vertex angle. Right? How do I distinguish one electron from 2? We'll see it in a second. We'll get to it in a second. But for the time being, we are, how long is this thing? 1 millimeter? 2 millimeters? 1 meter? Do you have a feeling? Again? Yes. So how long would you say it is? Wow. You only got it wrong by an order of magnitude. Not that bad. At least the guy is brave. So let's do it. It's called an exercise. Guys, you can do that. Use the better block formula. So the answer to the question is the electrons are going to move. They're going to ionize the gas. They're going to behave as MIPs, mostly. Not quite. They will Bergstrahlung a bit and things. But let's forget about Bergstrahlung. Let's assume that the guys move as MIPs, and MIPs just lose so much energy per unit. So we know how much. And then, of course, what happens, let's not forget the physics of these electrons. They keep ionizing the gas but they don't die graciously. When they have like 200 kV or so, they go through a region that we call the Bragg peak, where they kind of boom, deposit the energy. They die suddenly. So what we're going to see is like an ionization wire, very little delta rays, things, stuff, and then all of a sudden a blob of energy. We can compute the approximate size of the track by just computing how much energy we lose per unit length. And for that, we use the formula of beta block, and there you have the formula of beta block. Do the calculation yourself. Okay? And tell me what do you get. Okay? But I'll tell you what you get. You get about 10 to 15 centimeters, the track. So you just got it 1 order of magnitude wrong, not bad. It's fortunate, because if I had to live with tracks, actually, you're not that wrong. This is the reason why I need to use 10 or 15 bars. If I would go to 1 bar, the tracks would be 1 meter long. And then hell, I will need a detector really big to contain my tracks. So pressure is making everything miniature, which, by the way, also tells you something about I cannot go up on pressure forever, or eventually I run out of size, right? Fine. So we got more things. Now it comes energy resolution. Before we do the calculations on energy resolution, let's go to another classical experiment. And let me tell you something called the hidden Russian. You know what is the hidden Russian? It's no matter what in particle physics and nuclear physics, no matter what you do, there was always a Russian who did it first. And normally you didn't know because it was hidden. They published in Russian in some obscure journal. And it happens again and again and again and again. All right? So keep this in mind. Science does not know about politics, does not know about funny things. And Russian scientists, even in very non-optimal conditions, they were great. In the 50s, the 60s, the 70s, the 80s, you would go and say, okay, what thing I have discovered? No, hell, this guy did it before you. So Volobnikov actually was not a hidden Russian, fortunately. He was a very well-known public Russian, and he did this beautiful measurement. So they took a pressure, a chamber, in which they could increase the pressure to very high level. So you can, rather than writing pressure, you write here density. Okay? Now, let's keep one number in mind. Density of liquid xenon, 3 grams per cubic centimeter. Okay, it's an interesting number to remember. So this is liquid xenon, okay? And this is the density in gas detector, which is way smaller, 100 times smaller. So this is the region of gas detector at various pressures. So what can you see here is that to this density, which is order half of a gram per centimeter cube, nothing happens. The energy resolution, full width Hebb maximum is hell, small, okay? 0.4%, 0.3%, flat. And then zoom. And when you arrive to liquid xenon, you're done. So this is a beautiful measurement because when you extrapolate this resolution, which doesn't mean that you have the right to extrapolate, but you just do it anyway to see what happens, then you get that the intrinsic resolution that this measurement leans at is ordered of 0.3%. Not that far away from germaniums. Not at all far from bolometers. In the right ballpark. Good resolution. Great news. For the gas people. For the liquid people, yeah, well, something wrong is happening here. The resolution gets totally screwed up. Now, a lot of studies went into this. I don't have the time to explain you why this is so, but it is so. But we can get a very simple idea and also a caveat. What Volobnikov was measuring was ionization. So in liquid xenon, you are distributing. Remember what I showed you, S1 very small, S2 very big? In gas xenon, at high pressure, scintillation is of no importance. It's nice to give you a signal, but fluctuation in scintillation will do nothing to you. In liquid xenon, the partition is way bigger, which means that ionization will fluctuate to scintillation. And if you don't measure scintillation, this fluctuation kills you. But of course, you have one way around, which is to measure also scintillation and anticorrelate it. We'll come to this. So far, everybody follows me? So, as I said, spoiler, in liquid xenon, we can help this. But so far, in gas xenon, Volobnikov says, guys, go ahead and give it a try. That looks good. Good. So, we actually can compute what is the energy resolution that we expect in a gas TPC or in anything. We can write a little formula. This 2.35 there is to make your life unhappy. Remember, every time that somebody tells you, my resolution is so much, you have 2 ways to understand what they are talking about. First of all, look whether they say sigma or maximum. Second, look on their, or it's easier, you look on their label. If it says nexo, then it's sigma. If it doesn't say nexo, it's everybody else for width and maximum. there is a 2.35 factor. So don't get me that thing wrong. Okay? So we put this nasty factor. I hate this factor. But it's life. Full width head maximum is what it is. I don't need to explain you what is full width head maximum, right? You all know that. Now, we have a few factors here. This is the interesting thing, Fano factor. The Fano factor, it tells you what is the intrinsic fluctuation that you get no matter what. And there are some materials where the Fano factor is high, and what can you do? And there are some materials, germanium being one, where the Fano factor is damn small. So you can do really well, okay? Actually, I'm not totally sure that we have measured ever a Fano factor for germanium because the resolution is so, it's a tiny number. It's a tiny number. So in xenon, it's not tiny, but it's small, 0.15. So you have this irreducible Fano factor. If you would have nothing else, all right, then this would tell you this is the best resolution I can get. And actually, when you get the best resolution that you can get here, you get 0.3% for width maximum. Of course, you have fluctuations associated with the electronics and fluctuations associated to what? To the amount of light. Of course, right? And actually, we can look to the different factors and see what the effects are. This is Fano. So notice this. If I don't do anything, Fano gives me 0.3%. This is yield. So I want to get yield, which is, this yield is how much light I'm doing. This is the resolution associated with yield. So you can see that I need yield, which implies that I need to put amplification, which implies that I need to put electric field on my grid. So you follow the red curve and say, okay, when you put about 2 kilovolt per centimeter per bar, you are just touching Fano. So you don't need to get here because anyway you're going to be dominated. These things add in quadrature. You're going to be dominated by Fano. So you should arrive here, and then when you should arrive here, you add this thing, and this is the total. And the total comes about of less than 0.5%. So it's like, okay, if I do well enough, I can get 0.5% full width head maximum, which is a pretty number, and a much needed pretty number. So this is what our calculation says, and can you do that, actually? So this is the year 2011 or so. And in 2011, we went to Berkeley and built this beautiful thing, this size. And we put like 19 PMTs here. We put an electric field. We put high pressure on it, and we made the measurement. And this is what came. At 660 keV, which is the energy of the gammas of cesium-137, the large one, we got 1% full width head maximum. Look at this pretty thing. Now, if you extrapolate with the square root, 1 over the square root, right, to 2.5 MeV, you get 0.5%. So the measurement, the first measurement that we did with this prototype was really exciting, like, oh hell, we can get there, okay? So then we went ahead and did more things, but before I carry on, yes? Huh? We can see it here, the amplification field, not the drift field.
The amplification.
The amplification field. So this is the field that you put between the grids.
Right. Yeah. Right. So the E over P is the reduced electric.
Exactly.
But that also changes the drift velocity.
Nothing happens because the electrons move over 5 millimeters. And so the fact they actually accelerate, and changes on drift velocity that doesn't do much.
So the fact that you have a distance between S1 and S2, which is like...
We can play with, actually, you will see that we correct for those factors. Way more interesting than the change of the velocity is the geometry of the thing. You need to correct for the geometry. You need to correct for the fact that the grid doesn't need to be. So it is all kind of funny effects, of course. But the interesting thing, and the meat comes around now, is that we can correct for all that. That effect of the drift being a tiny effect compared with other things. We'll see to that. Before I finish, this thing was the basis. I just wanted you guys to have the fundamental ideas in your head. Okay? Now, obvious questions. Why in hell we didn't use something sexy, say micromegas, wires, all this kind of fantastic amplification system that the French invent? Why didn't we do that? Who can tell me that? Well, why are we being so boring with silicon PMs and stuff and not using, this beautiful systems, micropattern devices? Why? Well, the answer is avalanche multiplication. So remember, when we were crossing our region, it's just proportional scintillation. The guy accelerates a little bit, the velocity changes a bit, but nothing much happens. If you go into any kind of micropattern device, what you do is avalanche. Either near a wire or near a path or near whatever, you avalanche, you produce a mini shower. And those avalanches, they have their own fluctuations in gain. So from one to the other, you change. And the gain fluctuation is way larger than everything that we have been looking at. Why in hell everybody else has used for many other applications, the micro omegas and shit? Oh, sorry. Because they could. And why they could? Because the energy resolution was not 0.5%. Now, by the way, if you try to use a micropattern device in a high-pressure Xenon TPC, you will not have a problem with avalanche multiplication. You will have the problem that the thing breaks directly, sparks. Why sparks? Because Xenon is an opal gas. And as soon as you produce a shower, an avalanche, there is no mechanism to quench it. All the energy propagates, and then a spark jumps, and then you're done. Okay? So there are two ways around this. One is to use a micropattern that confines the avalanche so that it's kind of extinguished geometrically before it can really break the system. The other is to put a quencher gas. A quencher gas like CH4 that will eat the energy of the electrons and then limit the avalanche. Now, we have tried both things, actually. If you put a quencher gas, you kill the scintillation. This is what the quencher does. It prevents the scintillation from propagating. But if you kill the scintillation, you kill S1. But if you kill S1, you don't know where you are. But if you don't know where you are, then things that are shot by the cathode, all these nasty backgrounds of radon, you don't know. You cannot isolate them. So you're done. Sorry, you're done. If you put a micropattern device with pure xenon, you can barely live. We could live, but then your resolution is lousy. You have a resolution for width height maximum between around 4%. So you cannot live. So there is a Chinese experiment, claimed Chinese experiment, so far it's a paper experiment, but for many years these guys have been saying, we will do an experiment bigger and larger than X and anything else with micromegas. Now, keep me the secret, okay, here. While they were saying that, I was like, okay, fine. They have more money than us, they have more people than us, they maybe are able to buy tons of Xenons, but while they are insisting on using micropattern devices, we have no problem. But lately here, they are probably giving up on micropattern devices and considering EL, then I get worried. Because if you use an EL device and you have more millions than me, then you may have an experiment with an advantage. We will see how it comes, but please keep that in mind. In experiment, you need to make compromises. There are many TPCs around. For instance, the TPCs in Hypercamiocande or the TPCs in Dune, where you can for sure use wires, you can use gain avalanche, you can do all this. In neutrino-less double beta decay, you need the energy resolution, and you need S1. Without them, you are in serious trouble. Backgrounds kill you. So you cannot do it. You need EL. That was the great central idea that in the mid-90s, the Sankotar TPC started the game. They just put a small TPC in the Sankotar tunnel. They got nice tracks and stuff, but they were using wires, and they were using quenchers, and they were not even able to measure the 2 neutrino mode. In spite of the fact that they have everything nice, but without S1 and without the energy resolution, you just don't make it. So what changed the game was the realization that you could use an ELTPC. Okay? So this is okay. This is all explained. Oh, I still have more stuff to go. I thought it was the topological signature. Now, as we have seen, things propagate. Propagate. By the way, this thing that you see here is an idealized track. This is like the track if your detector could be perfect. You have a perfect camera, and then you would be looking something like that. You see the argument before about the vertex, the guy can even go into loops, all right? So multiple scattering will not let you know where you have one track or two, one electron or two, but your neural networks will. Train them, please. So, Bragg peak, 2 blobs. No Bragg peak, this is an electron, 1 blob. All right? So this is it. This is it. Is that a lot? Is that little? Well, it's a lot. Okay? And this is an interesting game because it tells you that we have some freedom. I can increase my pressure, nothing that bad happens. If I can make a measurement which is still good, because in reality this trajectory contains no information. All the information is something long with a head, a worm with a head, a worm with 2 heads. Okay, and this is a topological signature, and this is unique of high pressure xenon gas. It is about the only detector in the field that tells you the difference between 1 electron and 2 electrons. Okay? Now, let's think about how do you do physics with this detector. You are going to have all kinds of backgrounds. For instance, things that go from outside. So to start with, many of these things will just go through. Okay? Many of the low energy things will just go through because they will just not interact in the gas. The gas is relatively light. Okay? Some of them, the most dangerous one, will interact, but many will not. Then you could have something like one interaction, another interaction, one electron and another electron. Will this thing trick me? No, because I see these 2 things are separated in a space. Or I could have something that comes from a surface, from the cathode. Will it trick me? No, because I see it comes from a surface. So I can define a volume. See, this is my fiducial volume, saying nothing comes from surfaces. It has to be produced in the gas. And then the only background that I really need, external background, we'll talk about internal later. But the only external background I need to worry is high energy gammas. And high energy gammas always do 1 electron. So remember when we talk about perfect signature detectors? If my topological signature would be perfect, then, guys, with good energy resolution and with perfect separation between 1 electron and 2 electrons, done. Discovery. Yes? No background. Of course, the topological signature is not perfect. There is a number of times where the electron looks like 2 electrons. We'll get to that. Yes? So I hope the ideas are clear. You can see this formula. don't look so sad. You don't need to memorize it. Okay? Diffusion. Of course, nature is nasty. Did you ever understand that? Nature doesn't like to make your life easy. So it gives you a lot of stuff. Like xenon is a nice gas, and you can do all these kind of beautiful things with xenon. And then it wants payback. Yeah, but look, I'm going to diffuse your electron cloud. So you have seen this pretty thing. Well, it's not so pretty already because of the multiply scattering. But it gets worse because the cloud of electron gets more and more diffuse and it goes. The formula says that it's an exponential thing. So you can think as a Gaussian. You produce in any point a little electron cloud, and as the electron cloud goes to the anode, a Gaussians open up. Which means that you should imagine now my track a superposition of points, and each point is like a Gaussian. And when I come to the EL grid, I have something which has diffused, like a Gaussian superposition. It gets worse than that, because now I pass the EL light and I am starting to produce light all over the place. It's a second Gaussian. So the thing that I record is a messy image of my original track. It's like I have myopy. My detector actually has myopy. It sees the track, but not that well. Yes? Let's keep that in mind too. So, this is sort of actually what happens, not quite. But this would be my electron seen with perfect vision. When you convolute a diffusion and you convolute the EL effect, you see something messier. All right? But now it comes again that provided that my system is able to still remember the two endpoints, I don't care. I don't care that all these things are ugly and whatever. It's if the diffusion and all these effects do not mask the existence of two volts, I'm still okay. We'll get to that too. As I said, the blurring mechanism are the diffusion and the EL spread, and this ends up with the basic idea of high pressure lecture. Now we have all in hand conceptually, and we can move, we have until 1. We can move to the next lecture. Sorry guys, today I'm not going to give you a break. I'm going to keep going and going and going. And I don't want to see you watching your telephones or looking at the stars or even looking sad. So try to smile. The pain is less. When you try to smile, the pain is less. So carry with me. Let's go for the next lecture. Yes. The what? Sorry, I took my things and then I don't hear her. Yeah. Mm-hmm. They can cross. When they can cross, what you will see in the reconstruction, you can see all kind of fatty patterns. What you can actually, this question has two types of answers. One answer is it depends on your strategy. So first of all, the crossing of the electron does not need to reflect on the reconstructed track. For instance, at the microscopic level, you can have this thing, and then when I reconstruct something, I will just see poof, poof, poof. Second, crossing is not necessarily my problem. If I have a technique that allows me walk from one blob to the other. And third, it may even be less my problem than you think, and we will get to there eventually, because these days, when we started next, we had to develop an algorithm that we will discuss a bit to actually look for the blobs. So, and this is where it comes now. We need to deconvolute the track and do things. But let me make some spoiler. These days, you don't need this. You just tell a neural network to do it for you. Okay? And that simplifies life quite a bit. So let's keep this idea in mind, what happens with tracks that do funny things, and let's carry on with the following things, and we'll come back to an answer. So the next lecture has a title, and it's called Traum und Wirklichkeit, which for the German-speaking part of you is dream and reality. I couldn't resist to use that title because when I was a student, that should have been 1983 or 1984, there was this fabulous exposition in Vienna called Traum und Wirklichkeit, where it was exposed the Vienna of the beginning of the century, with Klimt making the Traum part, the dream part, and Wittgenstein making the Wirklichkeit part. So I was really impressed by that one. And so I wanted to tell you about dreams and reality, because the project next, compared with things like legend, is a baby. Germanium have been, as you have heard from Ricardo there, for eternity, right? Since the 60s. Germans are all as us. But Next has been around only for about 15 years. And this thing started, actually, we have the documents showing up what happened. This is Berkeley. This is a younger version of me. This is a younger version of my student Justo. Now he's already a researcher in Valencia. This is Dave Nygren, and this is James White. And so we met, this picture was around 2008. We met in Berkeley, and we wanted to talk about EL chambers. We were very excited because of all these Saint-Gothard ideas, and we have a new laboratory in Canfranc. We had to put something else. And Dave Nygren was like interested in playing this game, so we went there, and we came up with this. Again, you have already seen this. The interesting thing is that this was drawn not in the back of an envelope, in the back of a napkin. So we came up with the conceptual idea, and then we said, okay, easy peasy, we know how to, let's go home and do something. So we went home and did something. And in a few years, we built the first prototype, another younger version of me. Boy, the picture is really young. Huh? I mean, every time I get this guy looking at me back on the mirror, I say, okay, look at the picture. You will see, focus on this young guy too. It's an interesting picture too. This is the next demo detector that we built in Valencia, in IFIC. And this is the student of James White and other collaborators. So we built this first detector. And that happened in 2015. And by the way, that were the years that we made the first demonstration of energy resolution that I showed you before. So a few years more go on. In 2016, we put the first detector, the first large detector in Canfranc. Because these are lectures, I will save you the detailed description of what happened between 2009 and 2016. They were very, very dark years, all right? In which you're trying to make science when nobody believes in a new technology. Buy me a drink for dinner, maybe I'll tell you something about that. But this was already a detector larger than the Saint-Gothard TPC. It was radio pure, and we installed it in Canfranc. And this is what the detector was. So these are the interesting elements. You have the rings and the resistor that make up the field cage, right? You are inside, actually, a cylinder of Teflon. So the Teflon is providing a light tube so that the light can just reflect and end up either in photomultipliers here or in the silicon PMs there. So you have all the elements of your detector. It was like the realization of the original concept. The detector had a total mass of about 10 kilograms, out of which we really never put all the 10 kilograms inside. We never put the 15 bars. We just ran more of the time at 10 bar and about a few kilograms. And again, with the PMTs, you could measure S1 and S2. with the silicon PMs, you could make the positions, and therefore you could make tracks. Now, by the way, this thing that I'm showing you is not Monte Carlo. This is event 2018. So it's an electron, a real electron that we saw in the data. Hey, so the electrons in the data are looking good, right? So now it comes the kind of bloody parts. Your question. Now you get your signal to the EL, and you know, I want to get this very good energy resolution, but hey, wait for a moment. I have this extended track that goes in funny angles through the EL that shoots light all over the place for pi, out of which I recover only a fraction with my PMTs, which are on the back. Agree with me that every event is different? Depending on where I am in XY, I am going to record so much light, and it changes. Also, by the way, when I am moving along Z, there is an electron lifetime. The gas is not perfect. So some of the electrons will be eaten by the gas. So this lifetime needs to be corrected, and the lifetime appears to be an effect of losing energy. So how am I going to correct for all this? Now, secret. When we came up with the original concept, we didn't think on that. Which reminds me of Francis Halsen, who invented Amanda first and then Ice Cube. And Francis Halsen once told me that the only reason why Ice Cube, probably the most beautiful machine ever built by humans, right? 1 kilometer of ice instrumented, 1 kilometer cube of ice instrumented in the South Pole. Okay, beautiful as it is. He says that the only reason why this detector exists is sheer ignorance. Neither him nor any of his collaborators read anything about the propagation of light in ice. Fortunately, because it was well known, very well known by the time, that in ice light propagates a few meters only. And they needed light to propagate kilometers. So they built a detector with utter ignorance of that. Hell with that. And why in hell is this thing working? Because they were lucky. And why they were lucky? Because the ice of the South Pole is ultra pure. Nobody had ever measured such an ultra pure ice. And in such an ultra pure ice, light propagates kilometers. So there is a component in science of being lucky at the right moment. Anyone who has been in the business for a while will tell you. Ask yourself how lucky you are. This is a good thing. Now, confession, we didn't know how to correct for all those effects. We have vague ideas. The effect is big, but then the solution was in hand. What is the solution? You fill your detector with radioactive krypton. Krypton 83, is a noble gas, another noble gas. It will decay in a few hours. You pick up little ceramic pellets that exudate gas, and your detector gets totally filled up with krypton. Krypton decays, giving you a point energy of 40 keV or so, 45 keV. This 45 keV little energy point is like you fill your detectors of little energy points. And now you follow each one of these little energy points, and you say, okay, in this position, there was something of 45 keV, but I recorded 37. In this one, there was 44, but I recorded 44. In this one, I recorded 16, but there were 45. You make a map, a heat map. And you say, depending on which position we are, I have a correction factor. And you take millions and millions and millions of kryptons, and then you make a very detailed map. Actually, you also used to compute the lifetime, right? This guy was in this position, and I measured so much energy. Actually, both things are correlated, but they are sufficiently uncorrelated that you can decouple them. So we found ourselves with a technique that was known in the field, but actually came out to be extremely useful for us, probably most useful for us than for anybody else. The dark matter experiments do use krypton for their calibrations, but the amount of resolution that we needed was essential. So, by doing this, we were able to measure the energy resolution that we got with krypton itself, of course. And then we got about 4%. And 4% actually extrapolates to 0.5% of the corresponding energy. So again, the confirmation with a big detector, now this is a big detector after all corrections, that you can really get to 4.5%. Yep, that was good. That was very exciting. Then we actually use radioactive sources to measure tracks at high energy, at all the relevant energy, at 2.6, this is thorium gamma, this is double peak, this is cesium, and we got numbers that were not as good. Why not? We don't know yet. The resolution that we got overall, it fluctuates between 0.8 and 0.9. But actually, it's not dominated by the map, by the energy resolution, by anything. It's dominated by a funny effect, which is something that we call screening. It's like you have a track, and it always appears like the energy in the back part of the track is smaller compared with the end part of that, which should not be the case. It's like you have some electron screening, except that you don't have electron density for that. We hope that with X100, the next detector, we'll be able to understand this effect. The effect can be corrected, of course. You see here this kind of screening as a function of the length of the track. You see a little bit less backwards than upwards. And you correct by making another map, but then what you pay is for the residual of the correction. And then, okay, 1% is a very good number still, but we don't want 1%. We want 0.5%. And we now, we're in lecture 4, right? No, the target resolution was always 0.5 in the sense that 0.3 is the intrinsic resolution. We always knew we cannot get there. I mean, even when you make the simple calculation saying when I put so much EPIVA, 0.5. We know that we can get to 0.5 because we date it with cesium in the VDM. We do it with krypton all the days. In the other prototype we had in Valencia, we got to 0.6. So we know that we can get there. We just didn't get there with next one. By the way, Axel experiment in Japan, they also get to, it's a small detector, but they get to pretty interesting numbers, 0.6%, things like that. So we think that the target, which is 0.5, is doable, and it's actually part of our program to get there for long tracks. But I'm telling you things as they are so that you don't think that nature is perfect and that things happen like this. This effect, we have never been able quite to understand what it is. Is it physics of the gas? Is something on the electronics? We don't know. We don't know. We just correct for it, end of the story. Now, let's go back to the idea of the blurring. We have this track that can make loops and can do all kind of things, and it's a blur. So for many years, we work in blurring the signal. What it means blurring the signal? It is kind of, the concept is easy. You have a blur signal. Let's think on a single point. So you have a single point, then you have a blurring function, which is a Gaussian, and then you end up in a Gaussian. If you want to correct the signal, all what you need to know is the F. So the function, the blur, the thing, and then you apply the inverse transformation, end of the story. Right? Now, suppose that you have a track. What you can do is do this blurring thing like point per point. So you need to have a PSF. You need to assume that the PSF is regular. Actually, what you want to do is to measure the PSF. So we could propose an analytical form from the PSF, or which would be a Gaussian, right? Or we could simulate it. But again, Krypton is there. So Krypton is a point. We measure a Gaussian. So we measure the PSF using Krypton. And this is the way we do. We measure the PSF with Krypton. We actually have two PSFs to do. I'm kind of moving fast and skipping some of the gory details. Like you have, remember, diffusion and EL. So you have actually to measure a PSF for each one of them. You can do both of them with Krypton in some fashion. We do that, actually. And then you need to resolve the problem. The problem is very simple. You have, well, it's very simple, kind of. So you have a convoluted image, and your convoluted image, in reality, you want to get your original image, right? So you have an inverse problem type of. You guys know what is the kind of classical inverse problem in medical physics? So in medical physics, for instance, in PET, what you have is exactly this, right? You have the response of the sensors, and you want to know what is the original image. So you need to come up with a procedure that allows you to reverse that function. This procedure, cutting a long story short, actually, you could do it analytically, it will not work. Why not? Because of noise. All systems are noisy, and when you try to make an analytical transformation with a big matrix like this, noise comes in, you're done. It doesn't work. And then you use an iterative approach. So basically, you start with a function that you say, this is my first approach, and then I reverse the thing, and then I feed back the function, and I carry on until it converges. The details are in the transparencies. I'm not going to get into, and in the papers refer, but okay, it can get a bit sporty, but it's not very complicated. All what you do is to compute. You need to have your PSF. You need to have a first approach to your blur function, and you just keep going. And your first approach to your blur function, actually, you take one flat thing. And actually, the procedure is exactly, the thing is called Lucy Richardson, because they were the guys who actually came up. They were two guys. And they did independent work. And actually, this is exactly the same technique that you use to do inverse images in PET. Exactly the same thing. All right, so you do all these things. And interestingly, you can do all these things with data. Data meaning it gets you the PSF. And here this goes. So let's go to the application. Kryptons. Once we have developed everything, we start by measuring krypton. This is typical response from a krypton event. You get one silicon PM that is touched, quite a few others, and then when you interpolate the energy between the silicon PMs, you get this kind of blurry thing. And then you apply your deconvolution function. Boop. Okay? Now, the next thing is you have like two kryptons. One cloud, another cloud. Can you see them? Interpolation, deconvolution. Now, we keep going, and here you go. You recover the deconvoluted beautiful tracks. And you can see, answer your question, I am able to see loops. So the deconvoluted tracks was our first kind of super success in the sense that we actually had not really foreseen neither the problem, so the blurring was way more difficult than we expected when we came with the idea, nor the solution. The deconvolution was way more effective than we thought when we did the solution. So now, all what you need to do, please go ahead and tell me signal and background, will you? It's not very ambiguous, is it? When you blur the tracks, crystal clear, right? Of course, I cherry pick one of few that were beautiful, but it's not very difficult. Notice also that it is easier that I lose one, and then I lose efficiency, which is bad but not terrible, than I invent something here. Okay? It can happen, it happens, but the technique is powerful, and now all what you need to do is to plot the energy of this blob versus the energy of this blob. Blob 1 versus blob 2, signal. block 1 versus block 2, background. And this is just a 2D cut. Okay? So when you do this 2D cut, you can see immediately you kill the thing by an order of magnitude, at the very least. All right? There will be some tails that come in for sure. That not perfect technique, but it is powerful. Okay? So all this, by the way, is data. So that was the nice thing about NextWhite. It really showed us what we had in mind. And then we went up and built up the energy spectrum of this thing. And this is the data. This is the data. This is the various contribution sources. And by the way, we did with, this is another beautiful trick. Because this is gas. It's very simple. Well, not simple, but you can put gas, take gas, put gas, take gas. So you can start your experiment with depleted xenon. And what is depleted xenon? Xenon in which you have removed xenon 136. So no signal. So this is this. No signal. This is the 2 neutrino signal. We know that there is no signal here. We know there is no signal here because there is no gas with the signal. And then we put our enriched xenon. And we measure again. And then we subtract. You subtract the background from the signal. I mean, you can use the Monte Carlo still, but hey, no need. And when you do this, boom, you get the signal. Okay, of course, it was a small detector, and this thing still has big error bars and so on and so forth. With the next detector, larger detector, we'll do that beautifully. But then notice that this advances some of the ideas that I was asking you the other day. One problem that we all have now and in the future is you need to understand when you say expect one background event per year, per ton, blah, 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 blah. How do you measure this? Well, one possible way to do that is that you really run for a year or 2 years or 3 years with your depleted xenon, measure things, and then estimate what is your background and your ROI. Remember about the blind analysis? Everybody knows what is a blind analysis now, right? Like you are forbidden to look into this region. Now, Ricardo and company, they have the problem. I'm kind of kidding. But in a blind conventional analysis, I need to forbid the collaboration to look into the region. I kind of need to, okay, don't even try to look. This is forbidden. This is locked. This is encrypted. I can do a different blind analysis in Next. I just let you do whatever you want, but the gas has no signal. Now, do the analysis that you want, enjoy yourself, look at all the data, but once you fix the analysis, then you cannot touch it. And then we put the gas with the signal in. Okay, so this is another very sexy blind analysis that we can do played with having the gas with and without the signal.
This plot comes from the subtraction.
Correct.
But you could also do another plot. So using the xenon, applying the 2 blocks. So
Yes.
you should obtain more or less the same.
Actually, we do that, and we obtain more or less the same. And this is part of the games that we play. In this case, this comes from subtraction. We have a similar plot by looking for the 2 blobs. It looks very similar. And of course, this is kind of nice in the sense that it shows you your 2 neutrinos analysis. So, okay, so this is, I still have time, right? So, let me carry on. Okay, so
Can I take a chance to ask you a question?
sure,
On the layout of next one
yes,
and on the general idea.
yes.
Maybe I missed it, but why did you decide not to use ZDX all over the place, also for the energy?
Very good. This is an interesting question that is still kicking. Okay, so originally, when when the original idea of Next 100 of Next was conceived, if you look at the drawing that was done by hand by Dave, we had two possibilities, PMTs and PMTs, okay? And then I said, that was the idea of Dave, PMTs and PMTs. And then I said, oh, and the idea was with PMTs you make a barycenter. And I said, but with PMTs and PMTs we will not get a good tracking. And then Dave immediately took the napkin again and made cross fibers, like tracking. And I said, this is ugly. And this doesn't work. Yeah, but we don't have anything better. In 2008, 2009, silicon PMs, to start with, were an emerging technology. So people knew they were there. We were all interested, but nobody had never used them in massive thing. So the idea that you could just, and they were expensive. So EXO had used APDs. And again, APDs were nice, but in cold they work. At normal temperature, dark current is hell. So it was kind of, what do we do? And people from Zaragoza wanted to use Irigoyen Storzen Company, wanted to use micromegas. So the origin, in the year 2009, we didn't have idea of what to do. And then in 2009, I came up, that was in fact my specific contribution to the design, say, guys, let's put a plane of silicon PMs. And silicon PMs were completely new at the time. And it was, Dave was like, oh, okay, fine, let's do it. So at that moment, we didn't even think that silicon PMs were a decent alternative because the PMTs were guaranteed to give a lot of light collection, energy resolution, and blah, blah, blah. So we didn't think too much about that. But then later, obviously, after a little while, the question came also thinking in the future. So if you're going to make a big detector, why not use silicon PMs all over the place? So there is an obvious answer. There are two answers to this question. One of them kills it, the other one too. But the first one that kills the idea is that with silicon PMs, you need still to measure S1. And you are at normal temperature. And the dark current of the silicon PMs at 20 degrees is not small. Now, to measure S1, which is a kind of a small signal, you want to measure S1 and not only the S1 at the endpoint of the spectrum, you want to measure the S1 of krypton because you want to be able to tag tiny signals. And the S1 of krypton is, a few electron volts, 10 photoelectrons. And the dark current that you get when you put 1 million silicon PMs is way more than that. So if you want to use silicon PMs, you need to cool them. So actually, we thought in a model of NEX in which the gas was cooled right to almost liquefaction point. And at this stage, it sort of works. You reduce the current, the dark current to the level where you can see S1. But then it comes the second question. Why would you do that? Because the measurement of the energy on the silicon PMs indeed is doable. But you have a conceptual problem. You are integrating, but previously you are dividing your number in very little small steps. So energy, imagine energy as a pie, right? I want a system in which I divide my pie in the less possible number so that I can add up with the minimum error. In the case of silicon PMs, I say I have 20,000 silicon PMs. Then I have 20,000 small numbers. And now I need to put a cutoff to get rid of the diffuse light. And then I need to put a cutoff because of the electronic noise. And then I need to put a cutoff because, so I am propagating all kind of small systematic errors to a very large number of objects. The point is, correct. The point is here is that indeed the merit of the silicon PM plane is that it's kind of dense. The unmerit is that, first of all, you need a very large number of them. Second, each one of, if you want it dense, the silicon PFs need to be big. So big dark current per element. And third is that although apparently you cover things up, in practice, not that much, because the main thing goes there, but then it has all the diffuse halo. And you need to deal with that diffuse halo. And this diffuse halo introduces its own error. So it's not impossible. Actually, we run many studies of this, and actually there are still people in Next interested in this. And actually, this is the kind of thing that if tomorrow the guys from Nexo that are very great experts in big silicon BS would come and say, guys, we want to work with you, I would sit down with them. But the alternative that I will describe later, we think is simpler and better. Now, PMTs is not a good idea either. So let me advance this already. PMTs are messy. Actually, they are messier than you think. They are messy for two reasons. First of all, they leave holes. So you need to correct that. But this is not that important. Second, they are radioactive. They are damn radioactive. Okay? Third, their bases are radioactive. Gee. Fourth, they don't take pressure. And so because they don't take pressure, you need to separate them from your volume with something. But on the other hand, you want your volume to be very radiopure. So your back thing has to be copper, but copper is not strong. Gee. So you have a mess. So PMTs must go. Okay? End of the story. And I'll tell you later how they go. Okay? Meanwhile, we have 4 more minutes. It's all right. I think this was an extremely relevant question that will come again and again. And this is a great motive for discussion because the discussion is highly non-trivial. Like silicon PMs are kind of, the idea of the dense tracking plane is very attractive, right? I measure the position and the energy with the same system. And then it comes the small detail. This, to cut the long story short, would be doable, yes or yes, with a cool system. Because then we wouldn't have the problem of liquid system. But still, at normal temperature, it's messy. All right. Let me move to the lecture 5 that we will not finish. Actually, we will just introduce it. And this one is called Sailing to Ithaca. Okay? And Sailing to Ithaca, every time that you think on Ithaca, you think on what? A trip, right? Well, and we are all in a trip to the normal hierarchy. Why? It's a long trip. But Ithaca was also a long trip, right? So here is the Odyssey. Somewhere Ulysses goes to play to Troy and then makes this little work that you have heard about, right? And then goes all the way back and spends. So the way, in case you didn't make the calculation, a trip to Ithaca is exactly 20 years. Ulysses spent 10 years in the Trojan War, and then 10 years, in a small way back. This would take you normally 1 day or 2. He spent 10 years, but okay, he didn't have Neptune on his side. And also he made a couple of stops with Kirk and Calypso, kind of stayed there for a while. Maybe he wasn't feeling that bad there. The thing is that he took 20 years to come back. So it is interesting that neutrino experiments, I think that a trip to Ithaca is a good unit of measurement. Let's call TTI, trip to Ithaca, is a good unit of measurement for neutrino experiments. They tend to move in blocks of 20 years. The sooner, which implies that your career is just 2 trips to Ithaca, right? One example is, for instance, Kamioka experiment was commissioned in the 80s, got the Nobel Prize in the 2000s, right? And then 20 years later, we had like the Hyper-K next step. So 20 years is kind of the way the field moves, okay? not very fast. Right? We often get questions like, oh, so next 100 is already taking data. When are you making a discovery? And then you need to explain, okay, maybe 20 years, if we were very lucky, which for journalists is not that obvious. You better keep the numbers in hand. Now, here it comes another declaration. Every Odyssey started with a terrific idea. Of course, oh, jeez, I get a new device to conquer Troy, great. So we got this kind of new device to conquer neutrinos Dalvera decay. Hey, man, we are there. But there is two ingredients to an Odyssey. First of all, you need to get the idea. And second, you need to have utter ignorance of the complications ahead. Okay? So the Trojan War was messy. Neutrino Dalvera decay experiments are messy. I love this picture, looking for a needle in a high stack. Boy, if it were only so simple. That would be trivial. Any experiment today in the field would find the needle in the high stack. Like 1 day of data. It gets worse than that. All right? So this is kind of our road to Ithaca. We started with prototypes. Then we build next white. Then we're running next 100. As you can see, the thing keeps whoop, 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 scaling up. And then somewhere, maybe in the next decade, we will have a ton scale detector. So as you can see, there is a trip to Ithaca here. Whoops, not bad. And then another one. That's the way it goes. You guys are here. So you have one trip to Ithaca, or maybe two to go, so it's not bad. I'm going to leave the lecture in that point, but before we stop, let's look one more time to the idea of next 100, which is a scale-up version of next white. So you need something to shield the detector. We'll come back to the idea of shielding later again. So we have what we call the castle, the lead castle. You put lead all over the detector. You really close your detector inside a lead castle. Then you have your high pressure vessel, and then you have copper all over the place inside. Why is this copper there? It has to be very radio pure copper, because basically the gammas from the walls of the lab will shoot into the lead that will stop them. The lead will shoot into the pressure vessel, which the steel of the pressure vessel will also shoot, and the copper is there to shoot, to stop basically everything that comes from outside. And it does stop everything that comes from outside. You can always make it thick enough to stop everything that comes from outside, or almost everything that comes from outside. Of course, the copper itself has some radioactivity, so it will shoot you something. And it's important, because this afternoon we're going to discuss this, it's important that you keep this thing in mind. But also nice about the copper is that it's dense. So a lot of the radioactivity that the copper is shooting is eaten by the own copper. So at the end of the day, we only need to worry about, say, the last radiation length of copper in my system, sort of. Okay? Then the gas, and everything that is inside the gas is radioactive and a suspect. The PMTs shooting us, silicon PMs, these are sapphire windows. Sapphire is a very nice, non-very radioactive stuff. By the way, in our lingo, in the lingo of NEX, sapphire windows are not called sapphire windows, are called safari windows. Our engineer, the engineer that built the original sapphire window had her kind of special English, and then she decided it was safari windows. So the safari windows decouple the PMTs from the gas, and then we have a gas system that circulates everything there. And remember the idea, and this is the last thing that we're going to discuss today, we'll come tomorrow back to this. Remember the idea of an X white. Half a meter by half a meter, okay? About 12 PMTs, about 1,000 silicon PMs, fine. You scale up twice and twice. So 1 meter by 1 meter, then the number of PMTs scale how? A surface. And the background scales also a surface. More surface, but with a square, right? But the mass scales with the volume. So if I double the size, I almost multiply by 10 the mass. 2 to the cube is 8. So next 100 is a bit more than twice next white. And every time that you scale up a system like this, you win. Because you get a mass that goes with the volume and a background mass, and the signal goes with the mass. So roughly speaking, your signal goes with the volume, your background goes with the surface, so you're winning linearly. Or you wish you were winning linearly. But something like that is going on. So that gives you the merit of scaling up. Scaling is good. And of course, remember that once the next step will be, so we can already start, before we stop, discussing how will be the next detector, next HD. 1 meter by 1 meter, 2 meters by 2 meters. So you multiply again by 10 the mass, win again linearly with the background, and sort of easy recipe. We will see, it's not that easy, but let's stop here in the discussion of next 100, and tomorrow we'll carry on. Okay? Thank you.